Hello and welcome to Getting Started with Azure RTOS using STM32 microcontrollers. I'm Jacob Beningo and I'm here with Kristoffer, Martinson, and we are looking forward to telling you today about Azure RTOS and how we can use it in a microcontroller-based environment. Now, before we do that, I'm going to take a quick moment to tell you a little bit about ourselves. That way you know who you're talking to and who's sharing the information with you today. Now, my name is Jacob Beningo, as I mentioned, and I am an embedded software consultant. I run Beningo Embedded Group, and I've been working in the embedded systems industry now for about 20 years. My core expertise is in microcontroller-based systems, real-time systems, and I focus in a lot of different areas, actually. So I've had the opportunity to work in automotive, aerospace, defense. I've built medical devices, IoT devices, consumer electronics, and my core favorite and specialty, which is space systems. I do a lot of work developing flight software, along with working in a lot of those other industries to help people design their software architectures, how to architect their RTOS-based systems, along with helping them improve their software development processes. So I've also written a couple of books, one on reusable firmware development and one on MicroPython projects. And I also write periodically for design news and sites like embedded.com as well. So if you want to learn a little bit more about myself, you can feel free to hop over to beningo.com, and there's all kinds of resources and things you can learn over there. Now, why don't we introduce Kristoffer Martinsson here. He's the Senior Field Application Engineer at Percepio, and his core focus is in debug and trace tools for embedded systems. He's got currently over 15 years of experience in development tools, and he's going to share with us a little bit later how we can actually do tracing of our application code and catch issues while they're in the field. So it's going to be, I think, a pretty fun session for us today. We've got a lot we're going to be talking about. We're going to kick it off by me talking a little bit about the challenges that IoT developers are facing. I will then introduce you to real-time operating systems, along with a little bit of a brief introduction into Azure RTOS. I'm then going to walk you through how you can deploy Azure RTOS to STM32 microcontrollers. I'm going to show you a real basic example that should be pretty flexible. It's kind of a headless example that allows you then to get up and running really quickly. And then you'll be able on your own time to kind of go in and dig a little bit deeper and kind of build out on that into your own application. Then what I'm going to do is I'm going to hand things over, and Martinson is going to tell us about how you trace RTOS-based applications using Tracealizer, and he's going to introduce us to DevAlert, and then we'll give you guys some additional resources that you can use to further learn about Azure RTOS and also learn about real-time operating systems and debugging systems in the field. So there's quite a bit there for us, which I think will be quite a bit of fun here today. Now, before I do jump in and introduce the topic here for us, don't forget we do have a live Q&A session. So you're listening to the recording right now, but we've got 2 live sessions where you can answer all your questions, and we're happy to answer those. The first session is going to be on October 28th at 9:30 a.m. Eastern Time. The second session is going to be at 1 p.m. Eastern Time. Now, that 1 p.m. time did have a change. I had a conflict, and so we moved that forward 1 hour. So instead of it being 2 o'clock, it's going to be 1 o'clock. Okay, so with that in mind, let's get that introduction to why RTOSs are important to embedded developers, and really comes down to some of the challenges that are facing IoT developers. And when you look at the challenges that a lot of IoT developers are facing today, they can really be boiled down into 4 primary categories. The first one is security. Every IoT device needs some type of security, right? We need secure boot. We need firmware over-the-air updates. We need to protect our data, keep it private. Trying to figure out how to connect to the cloud connectivity. That's another challenge for a lot of developers. We're not cloud experts. We're experts in real-time systems. So how do we bridge that gap and actually develop applications that can talk to the cloud and handle all the networking and all that fun stuff? Second, we have low power, which is a pretty big issue. A lot of IoT devices are battery operated. Some of them are going into hard to reach places around the world, and being able to optimize that battery life is really important. And then finally, debugging. Debugging is one of the biggest challenges embedded software developers face in general. And when you add a connected piece to that, with IoT and everything, it can really get complex. We need to be able to remotely monitor our systems and debug them and update them and trace and really see what's happening. So what we're finding is that a lot of complexity today is driving the need for a real-time operating system in the embedded device. And then that it allows us to do a lot of cool things, actually. From the way that we architect our systems to the way that we actually debug them. And I won't give too many spoilers here. We'll dive in and kind of work our way up to understanding how these challenges are really driving the way that we design and build our systems today. Now, as I mentioned, real-time operating systems, I'm finding are really they're becoming the core of nearly every IoT device. There's enough system complexity there that to try to do it in bare metal, it can be done, but the complexity level of the code really starts to go up by a fair amount, magnitudes of order. So real-time operating systems are really creating that foundation. And what's happening with that as we stop and take a look at it, a real-time operating system it's basically a system that's designed to manage hardware resources for us. And it does so with very precise timing and with a high degree of reliability. So what this allows us to do is really architect a system that can be reused, that can be scaled very easily, but more importantly, that manages a lot of low-level resources for us developers so that we don't have to worry about them. And that's a huge advantage. A real-time operating system helps, as long as you design and architect your system right, really helps improve the reliability of the system, the predictability, the performance, along with the scalability of the system. And it allows us to also get concurrency, or at least the illusion of it, through multi-threading or multitasking type applications. Now, a typical RTOS that you look at is going to really be broken up into three main layers here. As you can see, we end up with some type of board support package at the very bottom, which is going to handle the specific hardware that we're running the system on. You then have the actual RTOS, which consists of a kernel, which is the scheduler. So most kernels will have several different types of scheduling. Preemptive scheduling is probably one of the most common, but you can also do round robin and time slicing and some other different techniques in order to design your application the way you need it to be. Sometimes a real-time operating system will also include some other exterior pieces. And what I mean by that is it'll include software stacks designed to really help you integrate and not worry about some nitty-gritty details. So for example, a good real-time operating system will often include a file system. It'll include some type of networking protocol. It'll include TLS and MQTT and things like that to really make things easier for you. They also might include some device drivers and device I/O. They might allow you, for example, to be able to interface to USB very easily. They also typically will provide you with some type of debug service that allows you to trace the application and see how it's actually behaving. So once you have that core, kind of that, you can look at an RTOS almost as a middleware piece to some degree. All the application then and really the high-level middleware then runs on top of that RTOS, and you design your application on top of it. So at least that's kind of where an RTOS fits in. And like I said, it can really help you reduce the complexity of your application and not have to worry about as much of the complex timing and some of the determinism that often crops up that you have to fight with and struggle with when you're working with bare metal systems. Now, the RTOS itself, that kernel, contains several different types of components that make architecting our system much easier, to be honest. So usually a kernel will include the ability to create tasks, which are essentially semi-independent programs that are running on the processor. So there's different ways that we can design those tasks to behave, but you can use things like preemption or time slicing where they take turns using CPU, or where they have priorities, and if you have a high priority task come along, they can stop the execution of an old task and start running something else. Now, in a bare metal system, you typically don't get preemption, even though you can kind of fake it using interrupts and things like that. So it's a very powerful technique that an RTOS brings to us. It also allows us to leverage things like software timers. Some of them are very tightly coupled to interrupt service routines, but they also give us things like semaphores, which can be used for synchronization, mutexes, which are used to protect shared resources, message queues, which are used to move data and messages around for inter-task communication, and also event flags, which can be used to signal that some event has occurred, like someone's pressed a button or a fault has occurred in the system. So there's also some other things like time management services and the ability to manage memory appropriately. For example, Azure RTOS has the ability to have memory blocks. So you have a memory pool and you can dynamically allocate memory, but you don't have the issues that are often associated with malloc, because of the way that they created deterministic memory management capabilities inside the kernel. All RTOSs aren't like that. If you look at an RTOS like FreeRTOS, for example, they do have memory management, but they're reliant upon malloc, which means that if you are using dynamic memory, you can end up with non-deterministic systems if you're not careful. You can also end up with heap fragmentation and several other types of issues if you're not careful. Just because you're using FreeRTOS doesn't mean you're going to have an issue if you architect your system appropriately. So, but the kernel can provide you those resources and those capabilities that make things easier for you to design and code your system. Now, again, real-time operating systems, there's lots of things that they're designed to help us do. They provide us with a mechanism for reliably scheduling tasks. Most of us are working with single core systems, So while we can get multitasking and multi-threading and the appearance of tasks running concurrently, it's just an illusion. You always have to have one task stop and another one take over the CPU, but you can design very good concurrent systems, even though you only have a single core system. As I mentioned, there's synchronization capabilities, memory protection capabilities built in, and those types of things. The real thing that you guys should be looking for when you select your real-time operating system is you want to look at kernels that are certified. A certified kernel can help give you the peace of mind that the system is actually deterministic, that it's designed, security was thought about up front, and that it meets some safety guidelines, or at least is pre-certified for those types of things. So that, in a nutshell, is kind of an introduction to real-time operating systems. Certainly, there's lots of other resources out there, so if you do want to learn more, you can always email me at jacob@beningo.com, and I'm happy to point them to you. At this time, I want to talk a little bit more about Azure RTOS and some of the capabilities that it provides before I run in and show you a good demonstration of how to get it up and running. Now, what is cool about Azure RTOS is that it comes with a wide variety of software packages. As I mentioned, an RTOS normally contains a kernel, but it usually has other middleware associated with it. At least the good one does. Well, Azure RTOS comes with ThreadX, which is a very good real-time operating system. It's been certified and pre-certified in several different areas like security and safety applications and things like that. It's one I've used in the past. I like it quite a bit. So maybe I'm personally biased. Just keep that in mind. But it's a pretty good RTOS out there. It also comes with USBX, which is basically gives you the ability to have mass storage devices, HID devices, and dual class devices. So it's a nice middleware software stack that you can use. And if you are creating devices that require connectivity to the internet, you can using NetX and FileX might be useful for you as well. So you can actually very easily get an SD card stack up and running. You use UDP communication, MQTT clients, and things like that. So lots of capabilities there that are built into Azure RTOS. And Azure RTOS, again, is kind of a collection of these four primary components that are then based on ThreadX, USBX, NetX, Duo, and FileX. Now, as I mentioned, one of the things that I really like personally about these things is that they include a professional-grade, highly reliable solution. So, for example, these software stacks in the RTOS are industrial grade. So, the networking stack is optimized for performance and uses multiple IoT protocols. There's also safety pre-certifications for IEC 61508, SIL4, and IEC 623L4 Class C, along with 26262, just as an example. So this is an RTOS and a set of software stacks that was put together with reliability in mind, which, coming from my background, again, kind of working in high reliability systems, that's something that I personally look for in a real-time operating system. Security is also important. If you're designing an IoT device, you got to have security. You got to think through your threat model and what type of threats you're going to be facing. Well, the Azure RTOS is already pre-certified for EAL4+, for TLS and DTLS, along with some software-based cryptography or cryptography. And the cool thing about this is that you don't have to worry about production licenses. STM32 does have a granted production license to be able to use Azure RTOS on all of their STM32 products, which makes it very easy for us to be able to leverage it successfully without having to worry about all those licensing issues. And in case you're interested in actually looking at the licensing terms, I've included a link here at the bottom of the screen that you can look at to understand what the actual licensing is. Okay. So I know this now comes to the point where I'm giving you a little bit of a background. I know it's kind of a crash course here to try to get through all the content that we have for you guys here today. But I want to show you how you can actually deploy Azure RTOS to an STM32 microcontroller. I think this is really important for you. And I hope it's one of those things you can walk away from this webinar with and successfully follow through what I'm going to do. We're going to show you here shortly, duplicate it, and then you can leverage that to build out your own applications. Now, so that you understand, there's several different ways that you can get Azure RTOS up and running, depending on the part and the package and everything that you're using. One of the common ways is to use the STM32 Cube, which has a configurator, an IDE, a standalone program, and also a monitoring tool. Basically what it is Azure RTOS comes into STM32 Cube IDE as a middleware, and then you can leverage that to then build out your applications. So it's pretty popular way to go about doing things. Now, for us today, what I ended up doing was I set things up in such a way that we can, I didn't want you to have to duplicate IDEs and setups and things like that. Microsoft actually has a really great getting started guide. It's a quick start guide that walks you step by step through how to get IoT Central set up on the Microsoft servers, and then how you can deploy a base build of Azure RTOS onto an STM32 device and connect it to IoT Central and actually send some telemetry data up to the cloud. So I thought that would be a great way for you guys to get started today. So that's what I'm going to walk you through here in just a moment. If you were to go and download the PDF presentation slides, you'll find that each of these here is actually going to, if you click on the PDF links, they'll actually take you over to the instructions I'm going to show you, along with links to like the development board and IoT Central port, the web portal. So those are the tools and capabilities we're going to be using. So let me now switch screens here, and I'll walk you through how we can set up Azure RTOS and deploy it to an STM32 microcontroller. The first thing that we need to do in order to get Azure RTOS up and running is we want to go and clone the repository. So as you can see here on my Windows machine, what I've done is I've pulled up the command prompt, and I'm going to make a call. I've created a folder called Azure where I'm going to clone my project into. And I want to do a recursive clone, and the address is just from GitHub. It's Azure RTOS to gettingstarted.git. So I'm going to go ahead and start cloning my repository here. Now what you're going to find is this is actually going to take 1 to 2 minutes. So what I'm going to do is fast forward the video here a little bit so that you don't have to sit through all of that. If you want to follow along, you could do the exact same thing and start your clone as well. All right, now that the cloning process is actually complete, what we want to do is make sure that we have all the tools that we need installed properly. Now, what ends up happening is that in order to build this, we need to have CMake, we also need to have ARMGCC, and then we also want to use a terminal to be able to see the output from the development board. Now, what I'm going to use is the Termite serial interface. But the great thing about the way that they've set up the repository for Azure RTOS is that it actually already includes these tools. So all I need to do is open up a window here. I can actually go over to my C drive. I had created a folder called Azure, and then what you're going to find is that you probably cloned into a folder called Getting Started. Now from this project, what we can do here is actually go in here, and what you'll find is that we can come under the tools folder, and what there's going to be is this git toolchain.bat file. Now what you do is you actually go through and run that, and it's going to go and it's going to download and install all the tools that you need in order to run the Azure RTOS and successfully compile it. Now I'm not going to go and run this bat file because I've actually already done this. So if I do run it, it's probably just going to tell me, hey, these tools are already installed, and not a whole lot of interesting things are really going to happen here. But that's okay. If you want to go ahead and do that, you can do that, and what will happen is the tools will start to get installed. Now what I want to do here is from my command prompt, and just to make sure that I didn't make any mistakes and that there aren't any issues, what I can actually do here is run cmake, and then I'm just going to run the version command. And what I should find is that it's going to report that I have cmake version 3.21.1 or whatever the latest and greatest version happens to be. So that at least verifies that I have the cmake toolchain there. Now, the next step of what we're going to do here is we actually want to open up the Azure Central portal, the IoT Central portal. And what that's going to do is we're going to go in there, and we're actually going to go ahead and create a build application. Now, what we can do here is I'll actually show you how that works. It might look a little bit different on my computer here because I've actually already gone through and done this. So I'm actually going to come over here to my portal, and I'm going to go to apps.azurioTcentral.com, and then I'm going to go ahead and click enter, and it's going to bring me to the IoT Central area here. Now, if you actually come over here and click on build, what you'll do is you'll actually want to create a custom application. So right here, what you do is you'd actually come in here and you would click create app. And then that would go ahead and it'll create a little application there. You can name it. For example, you could call it Getting Started. It'll give you a little URL. And there's an option to select a free 7-day trial for up to 5 devices. And then what you would do is you'd click the create button there. So let me go ahead. Let me try this again and kind of show you what this actually looks like. So I could come in here, for example, and fill this in. I might do something like I mentioned, getting started. I might, under here, you can see it automatically generate a URL, and then I'd want to create free. And then from there, I'd go and I would create this instance. So if I go ahead and create that, yeah, it's going to give me an error because I actually have already created this. So if I actually come under my apps, what you're going to see is I actually created an STM32 test area here. So what I'm going to do here is I'm just going to open up my existing application. Once you actually click create, you'd find yourself in a display that looks just like this. Now, before we start to configure our devices or do anything interesting, what you actually would want to do is come over to the devices tab here, click devices, and then you would click new. And what you do from here then is you can give your device a name. So for example, I might call this the STM32. It'll provide a device ID. We'd leave the template to be unassigned. And then you could go ahead and click create in order to create the device. So I'm actually going to, let me see what I did. Let's see what I named the old device. I call it STM32 IoT. I'm just going to create a second fake device here. I'll call it STM Live. And I'm going to go ahead and just create that device. So what you're going to see here is that I now have a second device here. You would actually click on this device then next. And what you could do here is come up into the upper left here. You'd click connect. And then what this will do is it'll generate connection IDs and keys that you are going to use when you actually connect your device. Now, these are generated randomly. Of course, I'm not going to activate my device since I've kind of just shown you what my scopes and my IDs and all of that fun stuff are. But what you would want to do is go through here and actually copy each of these and save them somewhere, someplace safe. Because what we're going to do is we're actually going to use those. We're going to copy them into our application. So for example here, well, actually not for an example quite yet, but there's a couple other things that we need to do. I want you to go through and copy those. That way you have the scopes and IDs and everything. And then what we're going to actually do is we're going to hop over into the code and we're going to modify the Azure config file with this information. So let me hop over there here in just a moment. All right, so what I'm going to do here is I'm going to get into the Azure getting started directory. There's actually under STM microelectronics. We're using the STM32L board. And then under this, I want to also go under app. And what you'll find here is there's this Azure config.h module. Now, what I want to do here is I'm going to just open this. I want to open it with, let's see if it'll give me my option here. If I can find it, open it with, and you know what, WordPad will be good enough here for me. Usually Sublime Text is in there or one of my other editors, but for whatever reason, it's not showing up here for the moment. And we'll just let that be okay. So what you want to do here then, as you come down here, what you're going to find is there's several areas we need to fill out. First of all, you need to look at your Wi-Fi SSID, and you'll put it in here, whatever it happens to be. So perhaps, you know, it's the Enterprise D, for example. Go ahead and put in there. And then maybe we have, you know, Picard for the password. Maybe you're not using WPA2. Maybe you're using, for example, a WEP interface. Then you'd go and actually replace this WPA2 PSK AES with the WEP. So you just got to make sure that your Wi-Fi mode properly matches what your local network is doing. So you put in your credentials. Then what you're going to have to do here is you come down here. You're going to notice there's some other areas here. I mentioned a little bit earlier, there's an ID scope, a registration ID that we found within our IoT Central app when we created the device. You'll want to copy and paste those two strings in there. And then you'll also want to scroll down here and replace the IoT device SAS key with the primary key that was generated for your device. Once you've gone through and done that, then at that point, you will be ready to rebuild your application. Now, again, we're doing this kind of I don't want to say it the quick and dirty way, but we're doing it in a headless manner where we don't need to rely on an actual IDE or development environment at this point. You certainly can always go and use, for example, Visual Studio Code and open up the folder directory and make changes to your application using Azure RTOS, or you could go and use STM32 Cube IDE or whatever your preferred IDE or editor happens to be. So once you've gone through and made these adjustments, you can go ahead and save that. I'm not going to put mine in because I've already actually done this. And then what I'm going to do is hop up into my Getting Started folder here. And if I get under Getting Started, I want to go under STM Electronics here again. And what you're going to find here is that under this directory, there is a there is actually a directory where we can rebuild the tool chain here. So under tools, I come under here and you can see there's rebuild.bat. So I'm going to go ahead and run that. It's probably going to tell me that there's nothing to build because I haven't actually made any adjustments. We'll see here what it actually spits out for us, but it might take a minute or so depending on your machine for it to go through and compile. So, all right, so under rebuild, it looks like it did a complete clean and it's going to go through and actually build the system here. This will probably just take a couple moments, so I'll just fast forward here in time so that you don't have to sit through this. All right, so now that it's completed the build, you can see here we get some output about the memory and things like that, but we can see that we were able to successfully create output files, so we were able to build successfully. I'm just going to press a key to continue, and at this point, we have now generated our binary images. Now, these images are actually going to be located a folder up here and under the build directory, and also under the app section here. So you can see here I've got some bin, elf, hex files, things like that. What you'll find here is that there's actually two different sets generated. You can see here there's a L4S5 that's generated. There's also an L475. So I'm using the L475 IoT development board. So at this point in time, it's okay for me to go ahead and actually plug in that development board to my machine. What'll happen is it's loaded as it just shows up as a drive. So what I can do here is I'm going to take my bin file. I'm actually going to copy this, and then I'm going to come over to the IoT board. You can see it shows up here as a discovery board, and I'm going to actually paste it into this folder. Now what happens here is, what's cool about the ST link is it also shows up as a mass storage device. So if I drop that bin file on there, it's going to copy in, and it's actually going to instigate or initiate a mass storage device bootloader. So once it sees that file's there, you can see here, oh, it closed out, and now it pops right back up. It actually took the firmware now. So now at this point, I should be ready to, the application's actually running. So what I want to do is I can open up Termite, and I've actually got Termite already running here just to save us a little bit of time. And you can see here that it's gone through, it's initialized DNS. It's actually in the process of connecting to Azure IoT Hub. And in just a moment here, we'll find we get to the main application, and then you can see here we've received some properties here, and now we're starting the main loop. So now our application is actually running, and periodically what it's going to do is it's actually going to send temperature data from my device up to the cloud. Now it's not real temperature data; it's just kind of fake data that's being sent as an example, but it's it's something at least that we're working with. Now we can actually verify that this is the data is actually connected to our dashboard by coming back into IoT Central here. And if I come back to my devices and I actually click on my device, my STM32 IoT device that I created earlier, what you're going to find here is I should be able to go to raw messages, and I should see that there's data coming in here. So right now you can see it's 10:07, and you can see here I've had a couple of telemetry messages come in displaying what the current temperature is. So that's pretty useful. I can also come over to overview, and you can see here's what the data looks like. Now, of course, I ran this example before I actually did the recording just to make sure everything would work the way that I expected it to. But you can see here the temperature slowly ramped up, and then it's going to kind of stabilizing, going up a little bit higher. So my board has been running for a little bit here. I'm not 100% sure if it's actually fake data or if it's actually an onboard temperature sensor. Given that this is the board really doesn't heat up that much, I'm not sure where it's grabbing the temperature sensor. I wouldn't expect 3 or 4 degrees Celsius to increase, which is why I thought it's probably fake data, but who knows. But in any event, you can see here, we can come in here, we can learn about the device, get data, see the raw data. If we wanted to, we could even, under command, we could go and send information down to actually trigger functions to be called on our device. I'll let you experiment with that a little bit, but for the most part, this is how we actually get up and running with Azure RTOS and connected to Azure IoT Central. So at this point, you're completely ready to go in and start making adjustments yourself. You can bring the code base into your own IDE, and you can start writing your own functions and customizing your own IoT device if you wanted to. I hope you enjoyed that demonstration and that you'll find some time later to actually walk through it yourself and then dig into the code. There's a lot you can do behind the scenes that I didn't show you, but at least this will get it up and running for you, and then you can dig in and modify the example and make it do what it is that you need it to do. So at this time, I'm going to hand things over to Kristoffer, and he's going to talk to you about tracing RTOS applications using Percepio Tracealyzer and also introduce you to DevAlert.
Hello, my name is Kristoffer Martinsson and I work as field application engineer at Percepio. So I am here today to talk about our support for Azure, and I have divided my presentation in two parts. The first one will be regarding tracing and Azure RTOS using Tracealizer. If you are using an RTOS like Azure RTOS or ThreadX, the complexity of your application increase. You have different scheduling objects, like tasks and threads and so on, and you have semaphores and queue and mutexes for communication and locking in between the different tasks and so on. So the complexity increase, and to really understand the behavior and debug your system on system level, you need to have some runtime insights. You need to have insight in what is going on in the application during runtime. You cannot just look at the source code and really understand the behavior, because it's almost impossible. So you need, or one way to do is to use RTOS event trace. And that is what we are working on at Percepio and our tool Tracealizer. So Tracealizer is it's intended to collect trace data or RTOS event trace and analyze it and visualize it in an easy way for you as a developer to understand what is going on in the system. And here I'm just showing a picture a little bit what our tool looks like. So regarding trace support in Azure RTOS, actually Azure RTOS or ThreadX has built-in support for Snapshot Trace, and they call their tool TraceX. And we at Percepio with Tracealizer, we have been supporting this for several years. And so you can take this trace file that is generated and read it and analyze it in Tracealizer. But this snapshot trace, that means that the trace data is stored in ring buffer in RAM. And as you then understand, the size of the ring buffer is limited. So for a Cortex-M class of device, the size of the ring buffer is normally measured in kilobytes. Maybe you have a 10 kilobytes available for this trace buffer and so on. So the size of the ring buffer limits the length of your trace recording. So if you have roughly a 10 kilobytes trace buffer, the length that you can record maybe is 100 milliseconds or 200 milliseconds. It depends on the application, how much trace data that is generated. But the benefits of using the snapshot is that you can use any debug tool to save this file, or save the ring buffer to a file, and this file can then be opened and analyzed in Tracealizer. So this is what has been supported regarding Azure RTOS or ThreadX since several years back. But from today, we are introducing streaming trace in Azure RTOS. So the next release of Tracealizer will include beta support for streaming trace. So what is streaming? Streaming is that the embedded software actually send the trace data to the host during runtime. So you are not limited to any size of any embedded ring buffer that you have in RAM. To be able to do this, you need to integrate our trace recorder in your application. And then you also need to define the streaming interface that you would like to use. We support several different streaming interfaces. Here I'm just listing some of the more common one for Cortex-M class of devices. And for example, you can use a J-Link with RTT. And you can, if you embedded or your Cortex-M device supports ITM and serial wire output, you can use that to output the trace data. But there are many other ways to output the trace data that we support. So with streaming trace, more or less you have unlimited tracing is possible, meaning that you can record for minutes or hours if needed. And here I just showing a screenshot from our tool where you can see that we have recorded roughly 1 minute and 31 seconds, and we have recorded roughly 3.5 megabytes of trace data. So this is just a very small application. It's not generating that much data, but here, as you can see, it's generating roughly 41 kilobytes per second, which is not that much. You could have application of a larger application. You could easily reach like 100 kilobytes or 200 kilobytes per second. So what does this look like in Tracealizer? So I'm going to switch to Tracealizer, and I'm going to open the live stream tool that we have in Tracealizer. So I have an embedded application, so it's a board with an STM32L4 device, and I'm running ThreadX or Azure RTOS on it. And I have integrated our trace recorder, and I've selected to use since I have a J-Link connected to this board, I can use RTT streaming on it. So I'm just going to connect to the J-Link and start the session here. So as you can see here, it starts to record trace data here. And actually, as you can see, some of the windows in Tracealizer are updated during the recording. That's because I have live visualization enabled. It can be disabled for some use cases where you don't want it. And as you can see here, we can more or less record forever. And I'm going to record here now for a while, so I'm going to fast forward here a little bit so we don't need to sit and look at the entire recording. Okay, as you can see now, we have recorded roughly 2 minutes, so now I think it's enough. So I'm just going to stop the recording here. And the trace is automatically opened in Tracealizer, but of course it's also stored on my file system, so I can open it whenever I want. So let's close this window. So what can you do with the trace data that has been recorded in Tracealizer? Yeah, I'm going to show you some of the different views that we have in Tracealizer, but I'm not going to show you everything because there is not time for that. But the first thing I would like to show you is the event log, and this is more like a raw representation of what is going on in the application. So this is what it actually is generated by the tool. So as you can see here, we see when the different threads are executing on what is going on. So here we can see that there is a context switch to the control task. And we can see that the controls task is sending some data to an HMI queue and so on, and it returns after 11 microseconds and so on. So we have a lot of different kernel events that we use to analyze and visualize what is going on in the application. And we also have timestamps on everything, which is very accurate timestamp since we're using a hardware timer or a cycle counter inside of the CPU. So let's go back to the trace view, which is the main view in Tracealizer, which actually shows you the different tasks and threads that are executing, but also interrupt service routines. So here we can see that we have a number of different tasks, and you see the names of them here, and we also have some interrupt service routine like the button ISR and some other interrupt service routine here. Right now we're just looking at 100 milliseconds of the trace, but we can zoom out here to see more. So as you can see here, we can zoom out as much as we want, but if you zoom out a lot, it seems like everything is executing all the time, but it's not. As you can see here, the control task is not really executing from here to here, but then it's executing quite a lot here in between and so on. But you can see patterns here in the execution pattern, and if you see something that maybe it's a strange pattern, you can then zoom in to that location. So I can, for example, zoom in here. And now we can see more details, but maybe I should zoom in even further, like that. So here it's easy to spot when the different tasks are executing and so on. And for example here, so what is it that we see here and what does it mean here? So let's take this example here. We see that this is the demo thread 1, and we can see it's not solid blue, but it's dotted blue here. That actually means, I can zoom in even further, that it's not really it would like to execute over here. This is it. Actually, it says here. So here it is when it would like to start to execute, but it's not allowed until here. So when it's more a solid blue here, but then it's actually complete almost immediately. And I can click on it and I can see that there are some, it seems like it's waiting for some semaphore here, and it actually blocks here, and so on. So, and the reason why it's not really executed down here is that there is a higher priority task here that's executing before. So it's both this one and this one that has higher priority. So here you can easily spot the different execution patterns and how different things behave, and if it looks strange why it's doing that, you can click on it and see the events and maybe then understand, okay, this was waiting for a semaphore or something like that. Okay, so this is the main view, and by the way, if you quickly would like to measure how long some time is, you can just drag like this, and we can see this was 3.8 millisecond in this case that I highlighted here. Okay, so let's zoom out here a little bit. This is the main view in Tracealizer. So it's combined the task and the interrupt service routine, but you also see the events that is generated. You have other views, and one of them is already open here. It's the CPU load graph that I see here. I'm going to zoom out here a little bit. So I see more or less the entire trace. So here we have the entire trace, roughly 2 minutes, and we can see the CPU load over time. So as you can see, most of the time the CPU load is just above 10%, but then we have some spikes here. And as you can see here, if I just click here, we can see that it's the button thread that's causing the higher CPU load in this case. And actually, if you would like to analyze it further, what was going on here, you can actually double click on it and you can see, okay, so in this period here, we can see that the button thread is executing quite a lot here for some reason. And if I click on some other place, here we can see that now in this time slot, the button thread is not really executing at all, and so on. So you have a correlation between all the different views in Tracealizer. So you can see, click in one and see what was going on in the other one, etc. Another view, and I think is very interesting in Tracealizer, is the actor instance graph. So I'm going to open this like this, and the actor instance graph can be used to analyze the runtime of a certain a certain task or thread. So for example, you can measure the execution times and so on, but I'm going to just select one of the tasks here. So I'm unselecting all of them here, and the execution time, that's the more or less the time it takes, how long it takes for the time from when the task starts to execute until it completes, when it goes back to sleep or waiting for a semaphore or a queue or something like that. That's how long, and it measures how long it actually executes. So it doesn't include the time when it was interrupted by some higher priority task and so on. So as you can see here, I'm going to remove the lines here. So as you can see here, most almost all the time this task executes in roughly a little bit more than 90 milliseconds. And I can double click on one of them here and zoom to that location and so on. But maybe this is not so relevant, because maybe the more relevant is to look at the response time. And what is that? The response time is, let's say the example of you have some interrupt that is generated when you receive some data. And you have a task that is, so it's waiting for some lock and for maybe a semaphore, and when the interrupt occurs, the interrupt routine sets the semaphore and it's time for the process or the task to process the data. And you have some requirements on how long it can take to process the data. So the response time is more or less the time from when the interrupt service routine sets the semaphore and until the task has completed and waiting for a new semaphore, more or less. That's the response time. So as you can see here, now it's not so stable at just above 90 milliseconds, because now the time here varies quite a lot, between just below 100 milliseconds up to maybe 115 milliseconds. And actually, again, we can check here what is going on. If I double click here, it zooms to this location, as you can see here, and I can actually zoom in here and see what is going on. And as you can see here, it's quite obvious why it took longer in this case, because there are several occurrences here when the task would like to execute, but there is some higher priority task that is executing instead. So here, for example, this one is executing, and in this time slot down here, you have several different tasks that are actually with higher priority that is executing. So this is just one thing you can do with the actor instance graph. There are other things you can measure periodicity and things that should execute in certain intervals and so on, but I don't have time to go through it all. So these are just a small part of the different views that you have in Tracealizer that you can use to analyze your ThreadX or Azure RTOS application. So I'm going to continue with my next part of my presentation. Okay, so the next part of my presentation will be about another product that we have that's called DevAlert. So let's take the case of that you have an IoT connected device. It could be using Azure RTOS that is most likely then connected to Azure Cloud for sending some telemetry data, and also, for example, you can have functionality for updating the firmware of the embedded device and so on. So let's take the use case of that you are pushing out a firmware update to your embedded device, and you suddenly see that some of the devices is not really functioning as intended. What would you do? This is where DevAlert comes in. So DevAlert is an extension to Tracealizer, you can say, and you by adding some software in your embedded device and connect it to our DevAlert cloud service, you can actually get feedback of what is going on in your application when it fails and so on. And we include a trace, software event trace, that you can open in Tracealizer to analyze what is going on. And one of the use cases is what I just described. So you have a deployed device, and let's say that you are pushing an update to it, and suddenly some of the devices, maybe not all, but some of them, seeing some sporadic errors, and you have no idea what is going on. With DevAlert, you can define alerts, that we call it, and that is an alert has certain types, so you can define as many alert types as you want to. It could be like a malloc fail device or a hard fault alert, or it could be some kind of user error or something like that. You can define all of these alerts yourself, And you can also add symptoms to it, which could be like where you are in the code, when the alert occur, in what function, and so on. But could also be any type of information that you would like to include in the alert. So when the alert is generated, you get feedback back to the development team, and it also then include a trace that you can open in Tracealizer, so you can see what was going on up until the alert occurred. Another use case for using DevAlert is in system testing. And in this case, the embedded device or the system that you are testing might not be connected to the cloud directly. It might have a debugger connected there, and whenever there is an alert is generated, maybe when a test is completed, the debugger reads out the contents of the trace buffer and all the other parts of the alert, and then it's forwarded back to some server somewhere. But it's still the same concept. It's just that it might not be the device is connected directly to the cloud in this case. So the same procedure is that this information is fed back to the development team, including a trace, so that they can analyze further why the test case failed and so on. So what is this product? What is the different parts of it? Yes, to the left here we see the device part. So you have your embedded device, and most in this case it might run Azure RTOS, and it could be connected to some cloud server, for example Azure IoT Hub or something like that. But in your embedded device you add a normal snapshot trace capability that are available in Azure RTOS, but you also add some other code for generating all of these alerts. And you then also need to define the different points in your code when you should generate an alert. But when an alert is sent to the cloud, it includes two different parts. You have some metadata, more or less some information about alert type, different symptoms, and maybe some firmware version and so on. But you also include the ring buffer, the trace buffer that you have in RAM. And this is stored in your cloud. So it could be, for example, Azure Cloud. So everything goes to, for example, Azure IoT Hub, but then, for example, it gets forwarded to some storage, some alert storage in Azure IoT Hub or Azure Cloud. And then some part of this data goes to our DevAlert service, but that's not the trace buffer and so on. It's just some metadata that we then can use to generate notification back to the development teams. And when they see the alert, they can just click on the link and actually download the alert from the trace from the alert storage. And what does this look like in Tracealizer? Yeah, I have opened another instance of Tracealizer here. And as you can see here, we have like a DevAlert console or dashboard here. So we can actually see the different alerts that has occurred here. You can also use the web console, which looks like this. It is similar. You see the different alerts and so on. And actually you can you see some more details of it, and you can see some of the symptoms that was passed to it, and you can also open the trace from here. And okay, but I'm going to switch back to Tracealizer and use this one instead. And I'm just having a short demo here. So I have an application here. It's an STM32L4 device, and it's running ThreadX or Azure RTOS, and it's connected to Azure IoT Hub. And it's, in this case, just sending some telemetry messages here now and then. And by actually just pressing a button on the board, I can introduce an error in my application. So let's do that. And as you can see here, it says user error. And what we do is that we disable the trace and generate the alert, and then we are sending the alert to the cloud. And then actually we enable the trace again, and let the application continue here. So let's see what it looks like in the dashboard here. I'm going to minimize this one. Okay, there you see, now the alert was up in our Dev Alert service in the cloud, and it shows here in the dashboard in Tracealizer. So as I said, you can also use the web-based console that we have. It works just the same, you will see it there as well. So we have a new error here that arrived just now. It's a user error, and by here we can see the latest trace, and we can see the device that was causing this one, this error. And by just clicking on the link here, we can download the trace from Azure Cloud storage. So I do that, and the trace will be opened. So it's downloading and just opening the trace like that. So that is it. So as you can see here, we have the trace. It looks similar to the example I've showed you before, but this trace is much shorter because it's just a snapshot buffer. It's just a few kilobytes. So you just see the last roughly 200 or 180 milliseconds here, what was going on in the application. But for example, what I can see here is that, yeah, TX semaphore put button semaphore, the meaning that the ISR, the interrupt service routine that's handling when I push the button, is actually generating or putting a semaphore, which is getting a new thread, which is the send alert thread that actually is waiting for this semaphore, and so on. So that is what is going on. So you can take a look at the trace, what was led up to the issue that you have in your application when this alert occurred. So that was all I wanted to show you here today. So it's back to you, Jacob.
Well, I hope you've all enjoyed today's session. I know we've covered a lot of material and given you a lot to think about, so I hope that you'll take a couple moments after this session to, first of all, make a short list of some action items that you want to follow up on afterwards and schedule some time to actually follow through on those action items. And then secondly, I hope that you will take some time to join us for the live Q&A sessions. I'm sure you have a lot of questions, or there's things you want to know about that we weren't able to cover during the live session here today. So I hope that you'll come and join us to ask those questions. Some additional things you can do to go further, starting with myself. You can hop over to Beningo.com. I have lots of useful resources over there. For example, I have an RTOS best practices guide that you can check out. I have some technology primers that I've done that are useful for people. I teach a lot of RTOS training courses. So if you're interested in learning more about real-time operating systems, you can hop over there and see what I offer, or you can even email me at jacob@beningo.com. I'll be happy to share some additional resources with you to help you get started on your journey there and get more familiar with real-time operating systems and working with Azure RTOS and cloud-based applications. I also have a blog and a newsletter that if you want to kind of stay in touch and see what I'm working on, or you want to continue to grow your own skills, you can hop over there and check that out. Most of those you can see what type of content is sent in there just by checking out my blog. Now, also for Percepio, there's several recommendations I have for you guys. First of all, you can hop over, try out Tracealizer yourself. They have a demonstration license that you can go out and get and actually run it on your own systems and get familiar with it. There's some links there for Dev Alert as well. They also have a really good blog. I really like how technically detailed their blog is, and also some of their application notes are fantastic as well. So I'd encourage you to kind of click on some of those links, as I mentioned in the PDF slides, and check out, and even just go to their website at percepio.com and see what they have to offer. One thing I know that they have started to do, which I've been enjoying quite a bit so far, they've only done one session so far, but they've created this webinar series on Runtime Insights. The next one is actually on November 2nd, and then they've been, have been posting where some of the next ones will be occurring at. But if you go to their website, you'll see this image off on the right-hand side. You can click that to register, or you can go to percepio.com/Runtime Insights register and sign up to be able to see those webinars. Once again, I just want to remind you, coming up shortly here at 9:30 a.m. Eastern Daylight Time And at 1 p.m. Eastern Daylight Time, we're going to have live Q&A sessions. So think up your questions and bring them out to us. We're happy to answer them and looking forward to interacting with you live in the Q&A sessions. All right, thanks again for your time and attention. We greatly appreciate it. I hope that you've learned a lot during this session. If there's other things you want to hear about, please feel free to email us. Let us know what topics will be useful for you in your own development. If you want to learn more about RTOSs or anything else, let us know. We're happy to, we're here to help and share insights with you guys to try to make your development experiences as smooth as possible. So we look forward to seeing you in the Q&As here in just a couple of minutes. Thanks.